So today in this lecture video, I'm going to go over section 8.1 and maybe I'll have time to go through section 8.2 as well. So you can see it's 1:39 now on Monday. I started recording the video during class or when class would have happened, but I was interrupted by the tornado warning. So I had to start over again. But I didn't really get that far. And it made me feel less ridiculous as well, because I thought I was being a little absurd and preemptively moving things online, but the tornado went off in the middle of or what would have been class, so I feel vindicated or a little bit justified. Because if we showed up for class, I would have had to cancel, and then you would have to stay in Ritter Hall or whatever. So it's probably better off that, or it was better off that I decided to move things online. Let me set a timer before I get into the content. And so, I mean, if you're watching this video, it means I've already sent out an email about some of the updates regarding like the final exam and the final exam review. So you should be able to find the final exam review on Canvas now. I'm sure by the time you're seeing this, I already sent out an email about that. And then there's like going to be an extra credit opportunity as well. That's detailed in that email. I haven't written yet, but you'll see soon. And so the exam for this class is Friday of next week, which is going to be May 8th. It's not like quote unquote cumulative, but you kind of need to know everything from the semester, and that naturally there's going to be problems where you have to do row reduction, problems where you have to find like the null space and the column space, problems where you have to find like eigenvalues and eigenvectors and stuff like that. Except they'll be kind of wrapped up in larger problems. So my intention is for the final, it'll be like any other midterm. It'll be 55 minutes, but you have 110 minutes to finish it because you have the full final time to do it. And it should be maybe like 5 or 6 problems or so. So I'll say more about it. There's going to be an exam review or final exam review. You'll be able to work through that. There's no homework due this week, so you only have to focus on the exam review. And then the only thing that's left is I don't know if there's going to be a quiz on Friday left or yet. It's going to be determined by how much material I cover. So if I finish this packet or the packet I put on Canvas, and there's like 30 minutes left or 20 minutes left of class, then there's going to be a quiz. And if it takes all of Friday to get through all of it, then that means there's not going to be a quiz pretty much. So I don't really know. The answer is there's probably not going to be a quiz, but there's a possibility there as well. I'll keep you updated. Okay, so kind of the last two major ideas in this class are going to be the idea of a linear transformation, and then we'll also talk about Markov matrices a little bit as well. This is something I just kind of have to talk about. I wanted to look more into applications, but if you have a linear algebra class and they don't tell you about linear transformations, then I feel like it wasn't as good a class as it could have been. So this is like just something that needs to be talked about in a linear algebra class. And it's really the reason why this is called linear algebra. It's because it's really the study of linear transformations, which can be represented as matrices, which is the perspective we've had throughout the entire semester. But there's another way of viewing things. And so thinking in terms of matrices, when a matrix A multiplies a vector V, it transforms V into another vector, A times V. So in other words, in goes a V and then out comes some A times V. So you can view this matrix multiplication A times V as some sort of function that's being applied to your vector. And so a transformation T follows the same idea as a function. And so the deeper goal is to see all of the vectors at once, which can be expressed as matrix multiplication. And so our definition is related to this idea here, where we can think of A times V as some sort of function applied to your vector. And so a transformation T assigns an output T sub V to each input vector V in your vector space uppercase V. The transformation is linear if it meets these two requirements for all V and W. So it has to distribute over addition. So it's a linear transformation if you have T of V plus W is equal to T of V plus T of W. So it has to distribute, T has to distribute over addition, like a derivative, or like an integral or something like that. And then you also have to be able to pull out scalars. So if you have T applied to C times V, you can pull the C outside, and it's the same as C times T evaluated at V for any scalar C. And so you can make these two steps or checks into a single check by just showing that T of CV plus DW is equal to C times TV plus D times TW. So it's showing you can distribute T over sums and you can pull the constants out. And so I said something along these lines earlier in the semester, but if you understand what's going on with the basis of a vector space, then that's really all you need to understand, because any vector in a vector space can be expressed as a linear combination of basis elements. So if you have any vector u in a vector space V, you can express it as a linear combination of the basis elements. And so the only thing you need to understand in order to understand what T of u is going to be is you just need to understand the image of T, or the output of T on V1, V2, and Vn, the basis vectors. Right, so you just need to understand what T does to basis vectors in order to entirely determine all possible outputs of T, which is nice because there's going to be infinitely many elements in your vector space, but you can understand only finitely many, or understanding only finitely many, you can understand all of them. Okay. And so just some other properties of linear combinations is that if V is the zero vector, then we have to have that T evaluated at V has to be equal to the zero vector as well. This comes down to the following trick. So if we have T evaluated at the zero vector, you can write the zero vector as a zero vector added to itself, because adding a vector to the zero vector doesn't really do anything. So, or I should say, if you add the zero vector to another vector, it doesn't do anything. So the zero vector is equal to the 0 plus 0, which, because T is a linear transformation, it means that you can distribute the T over addition. So this is the same thing as having T of 0 plus T of 0. And now if I subtract, well, let me condense the equality. So we have T of 0 is equal to T of 0 plus T of 0. If I subtract a T of 0 from both sides of the equation, that tells you that 0 is equal to T of 0, which is exactly what we wanted to show, right? So if you evaluate the zero vector or the linear transformation as a zero vector, you'll just get 0 back. That always happens. So this is a quick way of determining whether or not, or really, if you don't have a linear transformation, if you do like T at the zero vector and it's not, again, the zero vector, then it means you have problems. It's a quick, easy check sometimes to be able to say something's not a linear transformation. Okay, and so for this next example, we're really just messing around with the definition pretty much. It's asking which of these which of these transformations satisfy T of V plus W is equal to T of V plus T of W, and then which satisfy this linearity rule with respect to the scalars. And so there's two transformations that we have. The first one is the linear transformation that takes a vector and outputs the unit vector in the same direction as V. And there isn't really any reason to expect that this is going to be linear. And that if you look at the magnitude of V, it's going to involve the square root, and it's going to involve powers, or like the squares, which is going to be problematic. So this is not going to be a linear transformation really in both ways, but it's more obvious to see it from this perspective. So we're going to see that T of V plus W is not equal to T of V plus T of W. And the reasoning behind this is due to the fact that there's no reason to think that if you have the square root of something like V1 squared, or V1 plus W1 squared plus V2 plus W2 squared plus V3 plus W3 squared, there's no reason to expect that it's going to be equal to the following. So it would have to be equal to something like this. So we're really investigating the denominator of like this magnitude of V. So if you do T of V plus W, it means you'll have a magnitude of V plus W, which would be expressed as the square root. And there's no reason to expect that it's going to be equal to V1 squared plus V2 squared plus V3 squared, and then plus the square root of W1 squared plus W2 squared plus W3 squared. There's a lot of examples or numbers you can plug in to show this isn't always going to hold true, but I mean, it's just kind of clear, right? If you FOILed all this out, you're going to have like V's times W's. And I mean, you don't have like, you can't split up a square root based on sums or anything like that. So, like, this pretty much never holds. Like, you'll never have equality between this and this, pretty much ever. All right, so that's why this isn't really going to be a linear transformation in terms of distributing like T of V and T of W. And then additionally, if I did like T of CV or something like that, that would give you the vector C of V1, C of V2, C of V3, and then that's going to be over the square root of C squared V1 squared plus C2, or C squared V2 squared plus C squared V3 squared. And so you can factor out a C in the numerator and the denominator. This is V1, V2, V3. And then this is going to be C, and then you have the square root of V1 squared plus V2 squared plus V3 squared. These cancel out with one another. And so this is just going to be equal to V1, V2, V3. Rather than write it like this, I'm actually going to write it like this. This is the same thing as having V over its magnitude. And so this is equal to T of V, which is usually not going to be equal to C times T of V, right? It only happens when C is equal to 1, which means they're not really changing anything. And this makes sense because at the end of the day, what T does is it takes a vector and then turns it into a unit vector that points in the direction of that vector. And so the output of C times V should be the same as the output of V, which is generally not equal to C times T of V. So it's not linear in either respect. But if we look at the other transformation, we have T of V is equal to V1, 2V2, and 3V3. And so if I were to look, and if I wanted to check if this were a linear transformation, I would look at T of V plus T of W. And so it looks something like this. We would have V1, 2V2 plus 3V3. And then this would be plus W1, 2W2, 3W3. And so you add them component wise and you get a new vector. So this is just V1 plus W1. And then you're going to have 2 V2 plus W2 plus, or not plus, and then comma 3 V3 plus W3. And so this is just equal to what you would get if you did T evaluated at V plus W, right? Like the V plus W would just be the vector given by V1 plus W1, V2 plus W2, V3 plus W3 for its components. And then what T does is the first component is multiplied by 1, the second component is multiplied by 2, then the third component is multiplied by 3. So you would see that these two things are equal to one another, which means that it's linear in that respect. And then similarly, if I were to do C times T of V, this would be C times V1, 2V2, 3V3, which you can then distribute. So this is C, the vector given by C of V1, and then 2CV2. Actually, let me think about order. No, it would be 2 times CV2, and then 3 times CV3. And if I think about these vectors, we have C times V1, C times V2, C times V3, and then we're performing like this multiplication by 1, this multiplication by 2, this multiplication by 3. So this is just the same thing as being equal to T of C times V. Right, so you can have the scalar on the outside or the inside. It doesn't matter. The output's going to be the same. And so what this implies is that we have that T is a linear combination. Right, so that's an example of a linear transformation down here. And then this is an example of something that's not going to be linear. or it's not a linear transformation. There's no reason to think it is because this wraps up quadratics with like square roots and stuff like that. And it's not going to be very well behaved. What else do we got? Okay. And so the n vector rule illustrated in the second remark above leads to the most important fact about linear transformations. So I'm mentioning this remark that we have here, which says if you understand a basis, you understand all the outputs. And so if you know T of V for all the basis vectors, then you know T of U for every single vector U in the space. And so we can use these facts to compute the derivative of some vector U, or the derivative of a polynomial given by 6 minus 4x and then plus 3x squared. And so this is actually getting more into content from the next section, so section 8.2, but I want to say a little bit about it. So we're going to let P of x be the vector space. We haven't really had this perspective before, but we're going to let it be the vector space of quadratic polynomials. And so if you think about what would it mean to have a basis for the vector space of quadratic polynomials, well, you should be thinking there's going to be a constant term, there's going to be a linear term, and then there's going to be a quadratic term. And those things are determined by things multiplied by 1, x, and x squared. And so it's going to have the following basis. So it's going to be a three-dimensional space with the following basis where you have v naught is equal to 1, v1 is equal to x, and then v2 is equal to x squared. And then we want to think, we're thinking about the derivative here. So we want to think about what the derivative does to the basis elements. And so we get the following, we get d dx of v naught. V naught is just equal to the constant 1. So if we take the derivative, it's going to be equal to 0. If I do the derivative to v1, v1 is just equal to x. So the derivative is just going to be equal to 1, which is equal to v naught. So if you take d dx of v1, it gives you the other basis vector, v naught. And then if I do d dx of v2, v2 is equal to x squared. So this will give you 2x, which you can write as 2 times v1. And so you should be thinking, well, this is kind of getting into section 8.2 stuff a little bit. So, I mean, it's not a bad idea for me to kind of preempt that material by saying, this is kind of like telling you or describing what the null space of the transformation is going to look like. Because we're applying this transformation to a vector and it's giving us 0. So it's saying there's like some non-zero element that we can apply this transformation to, and we end up getting 0, or like the 0 vector in this vector space. And then these two are going to correspond to the column space, which will be more clear when we look at the matrix associated to this transformation. So the next section is all about matrices of linear transformations. So if this next part doesn't make a lot of sense yet, hopefully it will a little bit more in the next section. And so what we're really doing is we're taking a three-dimensional space, the space of quadratic polynomials, and when we apply the derivative, we're going to a two-dimensional space, right? Because we're taking something that has the highest power of x squared and going down to something that has the highest power of x. So the basis elements would be 1 and x. So we can say something like the following. So we have that the 3D input space, i.e. the quadratic polynomials, is going to be sent to the 2D output space via the following matrix. So we're going to have A. So how to think about this matrix A, and again, this is what we're going to do in the next section, but every column we should associate to one of our basis vectors, so V naught, V1, and V2 up here. And then when you think about what this transformation does is it sends it to either V naught or V1. So V naught and V1 serves as a basis for the space of linear polynomials. So we're going to have like 1 is equal to V naught, and then X is equal to V1. And so we've seen before, so how we determine the columns is the columns are really just going to be the coefficients that we have when we apply the linear transformation to our vector space or to our basis vectors. So if I do the derivative of V naught, this is equal to 0, which is equal to 0 times V naught plus 0 times V1. So you get 0, 0. With respect to V1, if we take the derivative of V1, it ends up being equal to 1 times V naught. So we'll have a 1 here. And then we don't have any V1 term here after applying the transformation, so it's going to be 0. And then if I take the derivative of V2, we get 2 times V1, and then that's plus 0 times V naught, so it's going to be 0, 2. And so how we can use this to determine the derivative of 6 minus 4x plus 3 squared is if I took this matrix 0, 1, 0, 0, 0, 2, and I multiplied it by a matrix formed by the coefficients that we have here. So this is going to be 6 minus 4, 3. If I perform this matrix multiplication, under the assumption that this is corresponding to V naught and this is corresponding to V1, then this is going to be equal to minus 4 V naught plus 3 times 2 V1, which can be expressed as being equal to minus 4 plus 3 times 2x, which is equal to minus 4 plus 6x, which is exactly, if you remember, like the derivative of this would be minus 4 plus 6x, right? So this is something we'll talk more about in the next section, but it's kind of starting that idea that you can express linear transformations as a matrix, right? So that's entirely what 8.2 is going to be about. But if this doesn't make complete sense yet, it'll make more sense in the next section. So like kind of this is just like a preview pretty much. This idea we'll expand upon a little bit more and talk a little bit more concretely, and eventually we'll be able to say or relate like what properties does a linear transformation have and what does that say about its corresponding matrix. Right, so we'll see more. We'll extend this idea further. And so this section is just more about like exposing you to this idea in the first place. So we're just going to look at more examples of linear transformations, and then we'll see what it does to vectors in the plane on the next page. So for this next example, it wants you to project every three-dimensional vector onto the horizontal plane given by z is equal to 1. And the tornado warning's going off. So I don't know. Maybe we'll stop here. Maybe I'll kind of jam them together later on. But I'm gonna stop there for now. And I don't know. We'll see what happens. Pretty much. Okay, I'm back. I was kind of like I don't know. There's like stuff going on up north, I guess, and it's making it so there's tornado alarms, and so I'm like, I may as well go down to the basement. But it's kind of like in a sense, it's like a false alarm, I guess. I think the bigger storms are supposed to come around like 5 o'clock or so. So I'm just gonna pick up where I mean, if you're watching this, it's almost like nothing even happened. But like I went downstairs and came back up pretty much. And so I'm gonna continue going over, I guess, the linear transformation stuff. I have like 23 minutes left according to my timer, so I'm gonna use those 23 minutes. So that way we finish everything in time this semester. So what we were doing is we're looking at more examples of linear transformations. And it was telling us, or what it wanted us to do is it wanted us to project every three-dimensional vector onto the horizontal plane, z is equal to 1. For instance, the vector xyz would be transformed to t of v, which would be equal to xy1. So you just change the z to 1 pretty much. And it's asking to see if t is a linear transformation. And you could go through the two axioms or the two checks where you're showing like it distributes over sums. You can take scalars outside, the stuff that's on the first page. Another way of showing that this isn't going to end up being a linear transformation, though, is I should be able to do t evaluated at the zero vector, and I should end up getting the zero vector back. That was this part right here. I don't even remember. It wasn't even that long. It was like this part right here. Oops. And then we'll see that's not going to be the case, right? Because what we're doing is we're projecting any vector onto something that has z is equal to 1. So this would be equal to 0, 0, 1. This is not the zero vector, so it's not a linear transformation for that reason, right? We need to have that it should be not equal to zero vector. So we need that t of 0 should be equal to 0, 0, 0. And we see that it isn't, so this isn't going to be a linear transformation. Plus, you can also think if I add two vectors of this nature together, it's going to make it so there's a 2 in the final component. So like the t isn't going to distribute over addition, which is going to be problematic. And so it's not a linear transformation. You can see it using this reasoning or some other reasoning. Scalars are kind of a problem as well. The next example, this is kind of what I was getting at in the beginning. So here it's saying we're supposing that A is an invertible matrix. And so this is going to be kind of the key observation. It's kind of the relation between matrices and linear transformations. We can show that multiplication by A ends up giving you a linear transformation. Because we know that if you do A times V plus W, we know multiplication distributes over sums. So this is the same thing as A times V plus A times W. And then further more, we know that if we did A times C times some vector V, we can move the scalar anywhere we want. So this is the same thing as doing C times A times V. And so just from these two observations, you can determine that matrix multiplication or matrices acting on a vector is going to serve as a linear transformation. And so you can also think about inverses. There's a lot of things you can think about, right? So another linear transformation is given by multiplication by A inverse, because it's just another matrix at the end of the day. This produces the inverse transformation, T inverse, which just brings T of V back to V. So if you do T inverse applied to T of V, you get that this is equal to V. And this matches the matrix multiplication given by A inverse times AV. So it's kind of like A inverse times A, we know that's the identity, so it fixes the vector. And so the kind of key question or the unavoidable question that we address in section 8.2 is looking at this question here. So the unavoidable question becomes, are all linear transformations from V is equal to Rn to W, which is equal to Rm, produced by matrices? And we're going to see that the answer ends up being equal to yes. And so this is an entirely different way of pretty much doing everything that we've been doing throughout the entire semester. So it's kind of like you're capable of doing linear algebra without really thinking in terms of matrices at all. You can instead just think in terms of linear transformations. And if you're familiar with the book Linear Algebra Done Right, which you probably aren't because you're not like a math student, or maybe you are, but I don't know, it's probably not on your radar, but it's like I'm doing air quotes right now, but it's like a famous, quote unquote, famous math book where they do linear algebra without like determinants and they avoid matrices as much as possible, pretty much. And it makes sense, right? If you're doing like eigenvalues or eigenvectors for a linear transformation, it's the same as saying you do like T of V is equal to lambda times V. So you can get like everything you need to know about eigenvalues and eigenvectors just from looking at linear transformations instead. And we're also going to see what you can say, like what being one-to-one or onto for a linear transformation, what does that say about like the null space and the column space of a matrix? There's like a rich interplay between the two is what I'm getting at, which we'll explore a little bit in section 8.2. The last thing I wanted to talk about from 8.1 was just looking at what linear transformations do. Right, so it kind of gives you a way of taking vectors and skewing them, translating them, moving them around in ways. And it's actually used a lot. Well, I mean, for instance, if I do something like this, like I'm just drawing an arrow on my tablet, when I'm moving this around, like the arrow around, it's really performing a linear transformation where I'm translating a vector to other places. If I shrink it, that's another sort of linear transformation. Then you can like skew it, change it, like rotate it, skew it, whatever you want. Like these, I'm just doing linear transformations. So that's all encoded within the tablet. And so this is kind of illustrated, I guess, in this portion, which I'm going to go through a little bit quickly because I want to get into how transformations relate to matrices more so. But to help visualize what linear transformations can do, we can look at a house that consists of 11 endpoints. So these 11 vectors are transferred into 11 vectors A times V. So we're taking a matrix and we're multiplying V by that matrix, which is really applying a linear transformation. And so A multiplies the 11 points in the house matrix X or H to produce the corners A times H of the other houses. So this is the house matrix. These are vectors. So the columns give you the vectors that end up determining the parts of the house that you end up having. So for instance, if you have something like 0, 8, it means you're going up. You're at X is equal to 0 and then Y is equal to 8. So you're going like vertically like this. So it kind of corresponds to this vector here. And then so each of these columns correspond to one of the edges of the house, really. And so in performing matrix multiplication on H via some matrix A, we're performing some sort of linear transformation. And so if A is equal to the identity and we multiply it to H, we just get the original house back. If we flip this, so that way the ones appear on the off diagonal and we have zeros along the diagonal, it's really like switching the X and Y coordinates with one another. And so you end up getting this house right here. So it's like a 90-degree rotation. You can have more continuous relations by using this orthogonal matrix we talked about earlier in the class, where you have like cosine theta, sine theta, and then minus sine theta, cosine theta. I think this was section 6.1 or 5.1 or something. I think it was 6.1. We talked about this matrix a little bit. It would have been 5.4 when we did the I'm lost. It was 4.4. That's when we did the Gram-Schmidt stuff. Okay. This is like an orthogonal matrix, which is like the rotation matrix. It just has the effect of taking your house and rotating it 35 degrees. And then this is an example of skewing the house. So it's like taking it and then like you're kind of shrinking it while also like squishing it at the exact same time. So you're taking each of the it's like the X and Y components and you're shrinking it down by a magnitude of 0.7. And then you're also performing like a little bit of a rotation of like 0.3 in some way. And so these examples, what do I actually want to do here? Maybe I'll give like a really brief answer to all of these just to say that I did it, I suppose. So for this first example, it wants you to tell, or how can you tell from the picture of T of H? So the transformation applied to H, i.e. like A multiplied by H, that A is diagonal, a rank 1 matrix, or a lower triangular matrix. There's kind of 3 parts to this. And so if you have a diagonal matrix, i.e. a matrix of the form where you're doing like, well, I'm not going to use lambda because I've been using lambda a lot, but you have like A and B. Like what this is saying is like you're really just scaling your X value by A and you're scaling your Y value by B without really rotating anything. That's what the off diagonal terms kind of do. And so what matrix multiplication would do onto our house is it's just going to lengthen the various, or lengthen or shrink, I should say, depending on if A and B are greater than or less than 1. But it's not changing like horizontal lines or vertical lines, right? So what this multiplication would do is it's going to send horizontal lines to horizontal lines. And then it's the same idea and that it's also going to preserve verticality. So if you have a vertical line, it's still going to be vertical. So you have something analogous for vertical lines as well. So it doesn't really skew things or like twist or rotate things at all, right? Like you're just scaling your X, scaling your Y, but not making like any sort of linear combination of X and Y at all, which is going to make it so you have like something more diagonal. A rank 1 matrix is taking something that's two-dimensional, and then if it's only rank 1, it's going to make it so it's going to be one-dimensional now. So it means it has the effect of squishing your house into a line. So the house ends up being squished to a line. It's either going to be vertical or horizontal, depending on where the rank is going to be. And then what a lower triangular matrix is going to do is it's going to skew horizontal lines. And then it's going to keep vertical lines vertical. So it keeps vertical lines vertical. Right, because if you're thinking about like what such a transformation does, right? Like it's going to look something like this. Right, so if you take some like x vector here or something like that, it gets transferred to like a11, a21. Like if I had the vector like 1, 0, it means that it's now going to be a11 units to the right and then a21 units upwards. So it takes like a vertical line and makes it so it has like something like this instead, right? So it makes it so it turns diagonal. Whereas this is just going to, like if you had 0, 1 here as like your basis vector, it's going to send 0, 1 to a22 times 0, 1. So it's taking a vector pointing upwards and it's still going upwards, except it's just scaled by a22. This one I care, I don't know. I don't really care about this example too much, I would say. So if you don't understand exactly what's going on, it's fine. I just wanted to do some demonstration or say a little bit about what's going on with these pictures here. Really, 8.2 is what you need to understand from this section. And I'm going to quickly go through this example and then say a little bit about 8.2. So this example, it asks, what are the conditions on the following 2x2 matrix to ensure that T of H will sit straight up? So this is just like we had before. It's really like part 1 of the previous problem. So in order to make it so, horizontal lines go to horizontal lines and vertical lines go to vertical lines, you just multiply it by a diagonal matrix. If you wanted to expand the house by 3 in all directions, you would multiply it by some scalar of the identity, which in this case is going to be 3. Right, so if I multiply by 3 times the identity matrix, this is going to scale the x components by 3 and scale the y components by 3, which is just going to expand the house by 3 in all directions. And then to rotate the house with no change in shape, this is the rotation matrix we talked about in section 4.4 when we we're doing the Gram-Schmidt stuff. So it's like cosine theta, sine theta, and then we have minus sine theta, cosine theta. Right, so we talked about this matrix in the past. So you should be thinking this is kind of like if you have 1, 0 here, this is like turning it into polar coordinates. And if you have 0, 1 here, this would ensure that at theta is equal to 0, you start at the point 0, 1, which is kind of like at pi over 2 almost. All right, so again, this stuff I'm not really going to ask about on the final, but it's worth talking about a little bit just to show you that these linear transformations kind of have the effect of rotation, translation, and then kind of like the skew effect that we have here, where you have like the linear transformation. Okay, yeah, that's it for 8.1. 8.1, you just really need to know the definition, and you need to be able to say whether or not something is or isn't a linear transformation. The more important stuff is going to be 8.2, which is where we're looking at the interplay that exists between matrices and linear transformations, which I hinted at a little bit before. And so in the previous section, I stated all linear transformations from some vector space V to a vector space W are produced by matrices. So in this section, we see why this is true. So we're going to go through with a construction of the matrix of a linear transformation, and you'll see it really isn't so bad. So the goal is we want to assign a matrix to any linear transformation T. And so for ordinary column vectors, the input V is going to be in the vector space V, and the output T of V we're going to assume is going to be in W, which is equal to Rm. So we're going from an n-dimensional vector space to an m-dimensional vector space. And so what we'll find is that the matrix A for this transformation is going to be m by n. Right, so m, again, is the output dimension, and then n is the input dimension. And really what's going to be the determining factor here is going to be the choice of basis in V and W. So that's going to decide what A is going to be. And so how is this matrix going to be constructed? So I'll talk in generality, and then we'll go through an example. And it's really going through an example that I think will make it a bit easier to see what's going on here. And so we're going to let V and W be the spaces described above. We're going to choose a basis V1, V2 up until Vn for V. And then we're going to have a basis W1, W2 to Wn for W. And so the matrix A is going to be an M by N matrix. And really, we just need to find out what the columns of A are going to be. And then you just fill out all the columns, and that gives you the matrix. So to find the first column of A, we apply T to this basis vector V sub K. Oh, there shouldn't be the first. There should be the kth. I think I originally wrote everything out in terms of the first column vector, but I wanted to write things out more generally. So to find the kth column of A, we apply T to the basis vector V of K. And I made the same mistake here. So it should be V sub K. So the output T of V sub K is going to be in W. And then I made the same mistake here. Some of them I swept up, a lot of them I didn't, it turns out. So if you do T of V of K, again, this is going to be an element in W, so you can represent it as a linear combination of the basis vectors of W. So T of Vk is going to be the combination given by A of 1k times W1 plus A of 2k plus W2 all the way up until W of mk and then Wn. So it gives you a linear combination in terms of the basis vectors of W. And so what fills up the kth column of A, the matrix corresponding to your transformation, are just going to be the coefficients or like the weights you have for your linear transformation. So these numbers A of 1k up until A of mk are going to be the columns or the entries of your kth column. And so this construction works because every V in our vector space V is a combination of the following form. And we know that T of V, because it's an element of W, is going to be a combination of the Wi's. And so when A multiplies the vector C, which is these coefficients in the V combination, we have that A times C produces the coefficients in the T sub or T evaluated at V combination. This is just from the fact that matrix multiplication is linear, just like T is. This will be more clear when we go through an example. Maybe I was just saying words and you're like, I'm not following. It'll make more sense when we go through an example. And so the matrix A tells us exactly what T does. So if we want to understand T, it suffices to just understand what's going on with A. And eventually we'll relate to the column space and the null space of A to characteristics of the transformation T. So every linear transformation from V to W can be converted to a matrix that depends on some basis. And so for this example, we're going to assume V and W are both three-dimensional. So we have bases V1, V2, and V3 for V, and then basis vectors W1, W2, W3 for W. We're going to suppose T of V1 is equal to W2, and then T of V2 is equal to T of V3 is equal to W1 plus W3. I don't know what T is a linear. Okay, sure. T is a linear combination. Sure. Oh, I guess this is just saying T is a linear combination, which makes sense to write down, I suppose. Anyway, so it wants you to find A, the matrix A corresponding to T, and it wants you to multiply by the vector 1, 1, 1. And then it asks, what is the output of T when the output is going to be equal to V1 plus V2 plus V3? These questions aren't going to be unrelated to one another. You can notice that the coefficients of V1, V2, V3 is 1, 1, 1. So one should tell us about the other. And so to construct the matrix A, again, we're going to use this interpretation that we have up here. So we have these V1s. We have V1, V2, V3. That's the basis with respect to V. And then the basis with respect to W is given by W1, W2, and then W3. And so we have that T of V1 is equal to W2. So this is, you can view this as being 0 times W1 plus 1 times W2 plus 0 times W3. So the weights would be 0, 1, 0. So you should be thinking like V1 is sent to 0 times W1, 1 times W2 plus 0 times W3, which is exactly what's written here. And then T of V2 and T of V3 are the exact same. They end up being 1 times W1 plus 0 times W2 plus 1 times W3. So the weights are given by 0 or 1, 0, 1, right? Because V2 is, or T of V2 is 1 times W1 plus 0 times W2 plus 1 times W3. And then we have T of V3 is equal to T of V2. So you get the same column over again. And so if I do A multiplied by the vector 1, 1, 1, this is the same thing as having 0, 1, 1, 1, 0, 0, 0, 1, 1, multiplied by 1, 1, 1. If I go through with this matrix multiplication, it's equal to 2, 1, 2. And so you might be asking, like, what is 2, 1, 2 actually saying about anything? Well, to see what this 2, 1, 2 corresponds to, we're also going to look at what happens. So that's kind of the first part of the question, right? It wants you to find the matrix A and multiply by the vector 1, 1, 1. So that's this part that we completed. And then we want to relate this answer to what we find when we do the output of T applied to V1 plus V2 plus V3. So if we do T of V1 plus V2 plus V3, because T is a linear combination, we know we can distribute over addition. And then we know T at each of these basis factors, right? T of V1 was equal to W2. T of V2 was equal to W1 plus W3. T of V3 was equal to W1 plus W3 as well. And so if I combine like terms, this is 2 W1 plus W2 plus 2 times W3. And if you compare the coefficients that we have, so instead of writing just W2, let's write 1 times W2 just to make it more clear. If you compare the coefficients that we have with what we have up here, you can see like we have the 2, which corresponds to this 2, the 1, which corresponds to this 1, and then the 2 here, which corresponds to this 2 that we have up here, right? So you can, there's two ways of going about things, right? You can find the coefficients by just plugging in directly into the transformation, using properties of the transformation to write things out in terms of the basis vectors of W, or you can convert to a matrix and reduce everything to matrix multiplication. In which case, these numbers here end up just giving you what the coefficients would be in the new basis that you're operating under. And so where I'll start class, I think I'm about over or out of time. My timer just went off. So I should stop now. And so what we'll do on Wednesday's class is we're going to draw more comparisons between the matrix of a transformation and the transformation itself. And if you are in principles of math, you know about one-to-one functions and onto functions. It turns out those kinds of properties on the transformation are going to relate to the null space and the column space of the corresponding matrix. So we'll talk about this on Wednesday. Hopefully the storm's not hitting you too bad or won't hit you too bad later today. And I'll see you on Wednesday.